I'd like to thank all the organizers for giving me an opportunity to speak at this wonderful conference. And also, this happens to be my last term at Waterloo in a span of 6 years now. And since there's lots of people from the CNO department here, I'd like to thank all of you for for being wonderful colleagues and creating a great atmosphere here. I'll definitely miss this place. Okay, so with that, let me start my talk. And this is joint work with Marcelo Carvalho, Claudio Lucchesi in Brazil, and USR Murthy. And it's quite recent. We've just put up the paper on arXiv a few months back with the same title. So if you're interested, you can search with the same name, show up. Okay. So 2 unsolved problems. Okay, let's start with one of those problems. Let me start with the perfect matching polytope. So here's our graph, the cube, and you've got a perfect matching there. And we can view a perfect matching as a vector over the edges. Ones where you pick the edges, zeros otherwise. And the perfect matching polytope is simply the convex hull of the perfect matchings. Okay, and it's clear that if you have a vector that is in the perfect matching polytope, then it has to satisfy 2 constraints, non-negativity, and that at every vertex, the sum of the edges incident at that vertex, sum of the values, is going to be exactly 1, because they're convex combinations of perfect matchings. Okay, and an observation made by Birkhoff-von Neumann, classical result, is that for bipartite graphs, this is if and only if. Right? Okay. However, this is not true if your graph is not bipartite. In particular, the standard example that you would see is the triangular prism, which is a complement of the 6th cycle. And here is the vector that satisfies those inequalities and equations, but it's not in the convex hull of the perfect matching polytope, right? Because you've got a cut here, and any perfect matching would cross the cut in at least one edge, and the sum here is 0. So that's not possible. Okay, so that's not good enough for general graphs, right? And we are going to say that the graph is Birkhoff-von Neumann if its perfect matching polytope is characterized exactly by the non-negativity and the degree constraints, right? Okay, so in particular, this graph is not Birkhoff-von Neumann. Okay. So the open problem, and it's a bit surprising that this problem is open till date, is to characterize the Birkhoff-von Neumann graphs. And what I mean here by characterize is to get a structural characterization that would lead to a polynomial time algorithm, or just get a polynomial time algorithm. Right. Okay. So let me show you a few Birkhoff-von Neumann graphs. See, clearly the bipartite graphs are in there. And one might think, well, maybe they are the only ones. That's not true. The odd wheels, Mobius ladders, and some other graph here. We'll talk about this graph a bit towards the end again. Right? So there are graphs that are not bipartite, but still Birkhoff-von Neumann. Okay. So let me just mention the following at this point. So we are trying to look at convex combinations of perfect matchings. Well, if an edge is not in a perfect matching, it's not interesting, right? We can just throw those edges away because they will never appear in any convex combination. So let us throw away the edges that are not in any perfect matching. And now your graph maybe disconnects. Look at the connected components. If we can characterize the connected components perfect matching polytopes, then we can characterize the whole graph, right? So that brings us to a definition. A matching covered graph is a graph that is connected and every edge is in a perfect matching. Right? And there is an extensive literature on these graphs. You can look up Lowas and Plummer, and there's a lot more work done since then by various authors. Okay. And it would be sufficient to characterize the Birkhoff-von Neumann matching covered graphs. And here is the smallest matching covered graph that is not Birkhoff-von Neumann, the triangular prism. Could it be that this graph has a special role to play in the characterization of these graphs that we are trying to characterize? Okay. So let me now tell you about a further reduction. So we've reduced the problem to matching covered graphs. Let me tell you about a further reduction to graphs called bricks and braces, which are special matching covered graphs. So here is a matching covered graph, and these three edges meeting that red line I've drawn is a cut such that every perfect matching meets that cut in exactly one edge. And such a cut is called a tight cut. If both the sides have at least 3 vertices, we're going to say it's a non-trivial tight cut. There has to be an odd number on both sides. And if you've got a non-trivial tight cut, you can do the following. You can contract one of the sides, or I'll call it the shore. You contract one shore to a single vertex, and you contract the other shore to a single vertex. And it is easy to observe that both these graphs would be smaller matching covered graphs because the cut we had was a tight cut. Okay. And we get smaller matching covered graphs, and so we can decompose the big matching covered graph into smaller ones until we've got a list of matching covered graphs that are free of non-trivial tight cuts. And these graphs are called bricks if they are non-bipartite, braces otherwise. Okay. And in fact, so that means that every matching covered graph can be decomposed into a list of bricks and braces. The big question that arises is, well, if I did this tight cut decomposition and one of you did this tight cut decomposition, then would we have the same graphs at the end of the day? And that is exactly what Lowas proved in 1987, that the tight cut decomposition is really unique. Okay, and that's great. Because it turns out that a lot of properties you can understand by just studying the bricks and braces. And this is exactly what's going on in this problem that we are looking at. Carvalho, Lucchesi, and Murthy proved that a matching covered graph is Birkhoff-von Neumann if and only if either it's bipartite or its tight cut decomposition is exactly one brick, and that brick is Birkhoff-von Neumann. And this decomposition can be done in polynomial time. So it suffices at this point to just characterize the Birkhoff-von Neumann bricks. Right. So that is our first problem. It's open, there is no polynomial time algorithm, no structural characterization. Okay. So at this point, notice that a brick, if you had a non-trivial separating cut, sorry. Okay, sorry. I'm going to call these solid bricks, and let me just show you why. So we are going to look at a co-NP characterization in the next slide, and that will explain why we are going to call these bricks solid bricks. Okay. And Carvalho, Lucchesi, Murthy proved in 2006 that the only planar solid bricks are the odd wheels. Right? So odd cycle and a universal vertex. Okay. So here is our brick that is not Birkhoff-von Neumann. And notice that we have a cut here. It's not a tight cut because there's a perfect matching that meets it on all 3 edges. But it still has a property of the tight cuts, that the 2 contractions are matching covered. They are K4 in this case. We are going to call such a cut a separating cut. So a separating cut may not be tight, but still gives you smaller matching covered graphs. And they observed, well, they proved that a brick is not solid if and only if it has a non-trivial separating cut. So in an odd wheel, for example, you would not be able to find a non-trivial separating cut. Similarly in Mobius ladders. Okay, and this explains why we call them solid, because you can't really break them into smaller matching covered graphs, right? So we're going to call them solid bricks. It's easier to speak than Birkhoff-von Neumann all the time. And let me tell you about another co-NP characterization that was proved by Reed and Wakabayashi. They never published it. A proof of it appears in the same paper of Carvalho, Lucchesi, and Murthy. And it says that your graph is not solid if and only if you can find 2 vertex disjoint odd cycles such that when you delete the vertices of these cycles, the remaining graph is a perfect matching. In this case, you get the empty graph for the prism that has a perfect matching. Okay. But you could have more interesting things. We'll see more examples. So both of these are co-NP characterizations. I don't know how to convince someone that a graph doesn't have a non-trivial separating cut, or it doesn't have 2 such odd cycles. Right. Okay. At this point, let me tell you a bit more about the importance of separating cuts in this theory. So we know the result of Jack Edmonds that to characterize the perfect matching polytope of any graph, you just need to add the odd set constraint. So for every odd set of vertices, you need to add the constraint that the sum of the x values over the edges leaving this set is at least 1, because any perfect matching will need to use at least one edge in such a cut. So those are the odd cut constraints. But in fact, so this is for any graph, so it's true for any brick in particular. However, for bricks, you don't need all the odd cut constraints. Carvalho, Lucchesi, and Murthy proved that you just need the odd cut constraints for the separating cuts. So, in particular, for the triangular prism, the only odd cut constraint you need is the one we were looking at. You just need this one. For the Peterson graph, you just need the odd cut constraint. For this one, there are 6 ways of doing this because there are 6 perfect matching in the Peterson graph. So you need 6 odd cut constraints. Each corresponds to a separating cut of the Peterson graph. You need the non-negativity and the degree constraints, and that is all you need. Okay. So in particular, if your graph had no separating cuts, then you wouldn't need any of these constraints, and that is exactly what the solid bricks are. Okay. So that's one of the problems we are looking at, characterizing the solid bricks. Let me tell you about another problem which comes from the theory of matching covered graphs. So let me start with this example. In this graph G, you see a blue colored subgraph H with the property that when you delete the vertices of that subgraph, you're left with 4 vertices that has a perfect matching. That remaining graph is a perfect matching. We're going to call such a subgraph conformal. If you delete the vertices of the subgraph, the residue has a perfect matching. Okay. And in particular, in this case, the blue subgraph is a subdivision of the triangular prism, but not just any subdivision. It is a subdivision where you replace each edge by an odd length path. So any such subdivision, we are going to call a bisubdivision. And so here you've got a bisubdivision of the prism that is a conformal subgraph. And we are going to say that the triangular prism is a conformal minor of this graph G. If this is your first time seeing this definition, it may seem a bit strange, admittedly. However, this notion comes up a lot in matching theory, and it's related to the ear decomposition theory of matching covered graphs. Conformal minors are closely related to matching minors, which have been studied very well. And in the case that your graph is cubic, like the triangular prism, these two notions coincide. Okay. But anyways, we'll be talking about conformal minors because we're looking at a cubic graph. And this definition, of course, you can replace the prism by anything else, and the same definition holds. So Lowas proved that every brick contains either a triangular prism or K4 as a conformal minor. And the result of Lowas is more general. It's true for all non-bipartite matching covered graphs. I won't go into that. We'll stick to bricks because we only need to solve our first problem for bricks. Okay, and this theorem of Lowas leads to 2 very natural questions. Characterize the triangular prism-free bricks. What I mean is those that do not contain the triangular prism as a conformal minor. Likewise, characterize K4-free bricks, but I will focus on the prism-free in this case. Okay. And our first problem was to characterize solid bricks, or the Birkhoff-von Neumann bricks. And by the result of Reed and Wakabayashi that I mentioned earlier, one can easily see that every solid brick has to be prism-free. Why? Supposing your brick is not solid, well then, okay. Supposing your brick is prism-based, I'm going to contrapositive. Supposing there is a triangular prism by subdivision as a conformal minor, which means when you delete the vertices, there is a perfect matching in the residue. There is some subgraph like that, there's a perfect matching. Now, I can extend this perfect matching. Now I've got a perfect matching after deleting 2 vertex disjoint odd cycles. And according to the result of Reed and Wakabayashi, that has to be a non-solid brick. Right. Okay, so every solid brick is prism-free. That just follows from the result of Reed and Wakabayashi. Okay. And that, well, so let's talk about the second problem, prism-free bricks. The first problem has been solved for planar, and we solved the second problem for planar bricks as well. So we proved that the only prism-free planar bricks are, well, you expect the solid ones to be in there, so you get the odd wheels for free. What else do you get? Turns out you get one more infinite family called the odd staircases that plays an important role in the works of Noreen and Thomas. So you get the odd staircases. What are these? Take a prism and subdivide the top two edges by an equal number of vertices, 1, 3, 5, odd number. And then we want a planar brick, so we're going to put a perfect matching between those vertices in the natural manner. So that gives you an infinite family called the odd staircases. Okay, so you got the odd wheels, the odd staircases, and there's one more graph, the tricon. This is it. The planar prism-free bricks are all of these. Okay. So what about the non-planar case, right? So for both of these problems, solid bricks and prism-free bricks, we've characterized the planar ones. So the problems that remain to be solved are the non-planar ones. And we prove our main result here is that these problems are essentially equivalent. Well, they are in fact equivalent. What I mean is, let G be a non-planar brick, then it is solid if and only if it is prism-free. This statement is false. There's one exception. Anyone? There's one exception to this statement. Any guesses? Peterson graph, of course. Thank you. You got the Peterson graph. Okay. So that's the main result, and that proves that these two problems are equivalent. We haven't solved the two problems, but they're equivalent. Okay. So let's see. Let me just state the results slightly differently. Supposing you have a brick that is not solid, then there are four outcomes. Either it is an odd staircase, the two of the outcomes are planar. It's an odd staircase, or it's the tricon, or it's the Peterson graph, or it contains the prism as a conformal minor. So any brick that is not solid, that is not Birkhoff-von Neumann, has to contain this graph, the smallest counterexample to the Birkhoff-von Neumann observation, as a conformal minor. The only exceptions are the planar ones and the Peterson graph. Right. Okay. So let me just say briefly about an outline. I'm really not going to go into the proof here. So what we prove as a first step is to show that any non-solid brick contains one of four graphs as a conformal minor. The first graph is the smallest odd staircase, bicon, or the tricon, or the Peterson graph, or the triangular prism. So every non-solid brick is going to contain one of these four as a conformal minor. Okay, that's our first step. At this step, we use a result of splitter theorem for bricks that was proved by Noreen and Thomas to deduce our main result. So we have a non-solid brick, and it contains one of these four. The result of Noreen and Thomas says that unless your graph belongs to a certain infinite family, that infinite family includes the odd staircases. So unless it is the odd staircases, you can build your brick starting from one of these four guys by doing certain operations, because this is a conformal minor of your brick that you're trying to build. These four graphs are all cubic. If you start building from the triangular prism, you're going to get the triangular prism as a conformal minor. If you start building from any of these, then because these are cubic, the only operation you can do among the four operations in the result of Noreen and Thomas is adding an edge. You've got to add an edge, but as soon as you add an edge to any of these three graphs, you get a prism in the resulting graph. So in your generation procedure, you're going to start from one of these three, you're going to add an edge, you get a prism, and the prism is going to be preserved forever. So, okay. All right, so that's a bit about the proof. We really use this very strong theorem, the splitter theorem. It's similar to splitter theorem for 3-connected graphs that was proved by Paul Seymour, and this is the one for bricks. So you need to do something, the operations are more restricted, because one thing you need to preserve parity. Okay. So now that we know about this, let me tell you a few more interesting things and state some conjectures. Well, just one conjecture and end with open problems. So let's go back to the result of Reed and Wakabayashi. It gives a co-NP characterization for solid bricks, right? So if you have two vertex disjoint odd cycles whose deletion leaves a perfect matching in the residue, then your brick is not solid. Well, in particular, you need two vertex disjoint odd cycles. If your graph did not have two vertex disjoint odd cycles, it has to be solid. So let's say a graph is odd intercyclic if any two odd cycles share a vertex. Right. So an observation is just that every odd intercyclic brick is solid. Okay. Now if all the solid bricks were odd intercyclic, we would actually be done. Because by result of Kaura, Bayashi, and Ozeki, these can be recognized in polynomial time. So it turns out that, well, every solid brick does not have to be odd intercyclic. There could be those that are not odd intercyclic. So let me show you an example of a family of such graphs. So how are we going to construct them? We start with the bipartite Mobius ladder, in this case K33. Let me replace a vertex by a triangle. That's not a brick. I need to add one more edge because that created a tight cut there. So I'm going to add one more edge. And that gives us the smallest solid brick that is not odd intercyclic. And you can do this on any bipartite Mobius ladder. So here's the bigger one, do the same thing, and you get another one. So that's one infinite family. Notice that in this infinite family, when you add that edge, you get a graph that is not cubic. You get high degree vertices, degree 4 in this case. We have another infinite family in our paper. I'm going to leave out that from here. And what's interesting is that we are not able to construct any cubic bricks that are not odd intercyclic. So maybe in the cubic case, these are the same. And if that is true, then these would be recognizable in polynomial time by the result of Kaura, Bayashi, and Ozeki. Okay. So let me just summarize. So the first open problem is to characterize the non-planar solid bricks, the Birkhoff-von Neumann bricks. The second one is the prism-free bricks, non-planar. And we proved that these problems are equivalent, the only exception being the Peterson graph, the only brick on Earth that is non-planar, non-solid, but yet prism-free. And so that's showing that these problems are equivalent. And I'll end here. Thank you very much.